Alright, let's try the first question here. The first question says, let me read it for you. It says, shown below are two charges which have the same magnitude but opposite signs. Points A and B are on the perpendicular bisector of the straight line that is joining these two charges. And the question is asking which one of the following is true about the direction of the net electric field at point A and at point B, respectively. So it says at both points A and B, the electric field will be pointing like this to the right. At both points A and B, it will be pointing to the left. C says it's 0 at point A and to the right at point B, 0 at A, to the left at B, none of the above. You have 1 minute. Please talk to the person next to you. This is about electric field. Remember, electric field is a vector. You need to have it vectorially to find the answer. So after you've thought of an answer, A, B, C, D, or E, you have to use the clicker to tell you the root. If the thing turns blue, that means your answer has been recorded. Yellow means that your response has changed. You can change your answer. So suppose you click on A, you can change your answer to B if you like later on. Alright? The only thing is, you have to do it within the time that I allot to you. Right now it says you have 1 minute to do it. Okay? As soon as I start the time, it will start showing that the time is decreasing. So for example, from now you have 1 minute. Everybody should start. Drop the person next to you, start thinking. Okay, so here is the response. It looks like most of you think that the electric field should be pointing to the right for both of these cases. Let's see if people are right or not, and actually it turns out that is the correct answer. Because if you remember what we had done last time, what we had said is that, okay, so if you have a charge over here and this is plus Q, you have a charge here, this is minus Q, and you're trying to find the electric field on the perpendicular bisector, right? At some point, let's say over here, or some point over here. This is what we are calling point A. Okay, so at point A, does everybody see that the electric field due to the positive charge will be pointing which way? That way. Remember, electric field due to a positive charge at any point will be pointing radially away from it. This is what we learned by putting test charges at those points. Do you remember? So at this point then, the electric field due to this positive charge will be pointing away from the positive charge like this. Let's call it E1. What about the electric field due to the negative charge? Remember, the electric field due to the negative charge at every point is radially inward. So if you ask me what is the direction of the electric field here, at this point, due to this charge, I'll say it's inward. Here it's inward, here it's inward. So at this point, it should be inward like this. So that would be the direction of electric field. Let's call it E2. Right? So do you see that if E1 and E2 are both pointing in the same direction, in this case, since they both have the same magnitude also, the charges have the same magnitude, E1 and E2 will also have the same magnitude. So the net electric field will have a magnitude which is 2 times the electric field that is produced by each of these charges at this point, right? You see, because these distances are the same also, right? You remember that the electric field magnitude was given by a constant K times Q divided by the distance squared. This is the electric field due to a point charge, the magnitude. Now, we have not been asked for the magnitude here. So this is the magnitude of electric field due to a point charge. Notice this is only true for point charge. So you can see that both of these electric field directions are the same, so the net electric field will be that way. Is everybody okay with that? Okay, what about at that point? What would be the direction of electric field at this point? This is point B due to this charge. Again, this charge, the electric field is radially away. So is everybody seeing that radially away? It would mean electric field is this way. Let's give it a name E1. right? What about the direction of electric field due to this charge? Anybody from the front row? Go ahead, please.
Inward.
Very good. It's going to be always towards the negative charge. So at this point, the electric field will be this way, right? Along the line, joining this charge to this point this way. Now, here is the thing. We have to add E1 and E2 vectorially to find the net electric field E, right? And so, now do you see that again, E1 and E2, will they have the same magnitude? Yes, they will, because both of them have the same charge Q, and this distance is the distance R, and this distance is the distance R for each of these charges. For this charge, this distance will be the R for E1, and for this charge, it will be this distance. Are these distances equal? They are. So we know that the magnitude of E1 and E2 are equal. Now, if you break, let's say that this is the X direction and this is the Y direction. If we break these electric fields into components, let's call this E1, then do you see that the electric field E1 will have a component like this and one upward? E2 will have a component like this and one downward. Right? Everybody's seen that if you have a vector like this and you break it into X and Y component, its components are going to be like this. Right? This is the resultant vector, E1. This is E1X. This is E1Y. Y. Similarly, your vector E2 will have components. This is your vector E2, and it will have components E2X and E2Y. So now, does everybody see that these two components cancel out because they are equal in magnitude and opposite in direction? So the only components that survive are the components along X direction. So E net will be like this. So is everybody clear that the correct answer is A? Any questions about this? Okay, let's move on to the next question then. So here is your next question. It says, a thin non-conducting ring, that means insulating ring, has three identical positive point charges which make an equilateral triangle with each other. The dotted triangle shows the imaginary equilateral triangle concentric with the ring with the same orientation as the equilateral triangle whose corners have the 3 point charges. So here is the equilateral triangle on which the 3 point charges are. These charges are equal in magnitude. Now here is some imaginary equilateral triangle. Now you have to find out which of these statements is true about the magnitude of electric field on this dotted imaginary triangle. A says it is the same everywhere on the dotted imaginary triangle because it has the same symmetry as the charges. It is the same everywhere on the dotted imaginary triangle except at the 3 vertices of the imaginary triangle. It is not the same everywhere on the dotted imaginary triangle because the vector sum of the electric field due to the 3 charges at different points on the imaginary triangle will be different. D says not enough information, and E says none of the above. Is everybody clear on what the question is? The question is asking about electric field at different points, here or here or here or here or here, at different points on this imaginary triangle, which is basically symmetric with respect to this triangle here. But remember, the net electric field will be produced by these 3 charges at this point or this point or this point or wherever you're considering, right? Is the question clear to everybody? Okay, so the question is asking about asking you to compare the electric field at different points on this imaginary triangle due to these 3 charges. Talk to a person next to you. Your time will start now.
They all have like different
It's alphabetical. Alright. It turns out that the correct answer is C. It is not the same everywhere on the imaginary. No. Yeah, it is not the same everywhere because the vector sum of the electric fields will not be the same at different points. Because what you have to realize is that the electric field is the vector sum of the electric field due to the individual charges. So if you have three charges, see you have some imaginary triangle. Now here is one charge plus Q, here's another charge plus Q, and here's another charge plus Q. There is no reason that if you just pick 2 points, let's say over here and over here, right? Let's try to find the electric field at this point. How will we do it? The electric field due to this positive charge, let's call it charge Q1, will be radially away from it. Do you see that E1 will be like this? Right? What will be the magnitude of E1? It will be given by K, Q divided by this distance square. Right? That would be R1. Okay, what about the electric field due to this charge at this point? It will be radially away from this because this is a positive charge too, and let's call it E2. And E2 will have a magnitude which is K, Q divided by this distance square because this is the distance R2 of the point from this charge, right? Similarly, the electric field due to this one at this point will be along the line really away from it because this charge is positive also, and we can give it a name E3, which is like this, and it will be K, Q, R3 square, where R3 is this distance. At this point, you have to find the vector sum of these three things. And of course, in order to find the vector sum, I will need to know what is the angle that each of these is making with the, if suppose I call this x-axis, call this y-axis, choose my coordinate system, I'll have to resolve each of these vectors into x and y component and find the net electric field, right? Okay, what about at this point? Now again, E1 at this point will be this way. E2 due to this one will be which way? Something like this, right? E3 will be, it will be again along the straight line joining the point on the charge, which is this way. And again, I will have to resolve all these three vectors into components, find what is the net x component, net y component. There is absolutely no reason to believe that even these 2 points will have the net electric field which is exactly the same. Do you see that? Why should we believe that KQ1, KQ over this R1 square plus KQ2 over R2 square plus R3 square, where all of these things are pointing in different directions, will somehow work out to be the same as these three? There is no reason to believe that. And so you can see that for 2 points it's not working. How is it going to work for all the different points on this triangle? So obviously the statement is not true. The electric field cannot be the same at different points on this imaginary triangle due to these three charges. Right? Any questions about this, folks? You have to understand that electric field is a vector quantity. Okay, let's look at one more question here. It says a thin, non-conducting ring has 3 identical positive point charges which make an equilateral triangle with each other. So here are the 3 identical charges again. Consider the imaginary dotted circle. This time this is a circle here, concentric with the ring, and 6 equally spaced points as shown. So point A is right above Q, point E is right, in a straight line with E, etc. Q is in a straight line with C, etc. It says the 3 charges are on the line segments connecting the center of the ring to points A, C, and E. Consider the following statements about the net electric field at the points on the imaginary dotted circle. So you have to think about now the net electric field at different points on this circle. One is saying the direction of the net electric field is radially outward. Radially outward means straight out from the center. Is the electric field at every point, whether I look here, 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 anywhere, straight out from the center? or not? Think about it. It's not just saying at some angle, it's saying straight out. The second one is saying the magnitude of the net electric field is the same as it is at point A at all of the 5 points shown. So at point A, B, C, D, E, F, the magnitude of electric field is the same. Is it true or not? The third statement is saying the net electric field due to the 3 charges at every point on the imaginary ring is radially outward. This includes those points not labeled. So is everybody clear? This one is saying the electric field is radially outward, that means straight out from the center at these 6 points shown. This one says at all points shown, and the middle one is saying the magnitude of electric field at all of the 6 points shown is the same. The question is asking you to choose all of the above statements that are true. Choices are 1 only, 2 only, 1 and 2 only, 1 and 3 only, 1, 2, and 3. Please talk to a person next to you. You have 1 minute to answer this question. Okay, so what do you think is the correct? It looks like people are all over the place. So let's think about this carefully, one by one. So you again have 3 charges, and these are at the vertices of some equilateral triangle, and then you have some circle which is concentric with the center of this equilateral triangle. You have 1 point which is point A, 1 point which is point E, and here is a point which is point C, and then we have point B right in the middle over here, we have point F over here, and we have another point D somewhere over here, right in between these two. Now here is the thing, will you be sure that the magnitude, let's first think about question 2. Question 2 is talking about the magnitude of the net electric field at point, and it's saying that it's at point A, it's the same as all the other 5 points that are shown. Is that really true? Will you for sure say that the magnitude of electric field at A is the same as that at E and C? How many people would at least be able to say that? That is definitely true, because if you see, point A has the same exact symmetry at point C and point E. Do you see that? Because point C is right in front of this charge, right? And this distance is exactly the same. And the distances from this charge and this charge are the same. And these angles are the same as it would be if you looked at this point. This one is just like the location of this charge. And these two are just like these two, right? Similarly, for this one, this point is like this, and these two are exactly like this. So yes, you will be able to say the magnitude of electric field at A, C, and E are the same. How would you find it? Again, if you decide to call this charge Q1, which is equal to Q again, and this is, let's say, this, let's call this Q2, which is Q again, and this is your Q3, which is Q again, then you can say, oh, the magnitude of electric field at C, for example, will be due to Q1, we can call it E1. E1 is like this. The magnitude of electric field due to Q2 will be, again, since it's a positive charge, it will be radially away from it. This is the direction of E2. The direction of electric field due to Q3 is going to be like this, right? my drawing is not very good, but the thing is, you ought to be able to draw a lot better than I am drawing here. But is everybody seeing that the vector sum of these three will give us the net electric field? Now here is the thing. We can see that the magnitude of the electric field at these 3 points will be the same, but is it the same as B? No, there is no reason to believe it will be the same as B, because B doesn't have the same symmetry as these points, because if you look at point B, what you will see is that this point will have its electric field like this. This thing will have its electric field this way. Let's give it a name E3, and this charge will have its electric field E1, which is this way. But notice something interesting. The interesting thing is that even though if I look at the component of electric field along the tangential direction, tangent to the circle here, or along the radial direction, that means perpendicular to the tangent, will you say that the component of E1 and component of E3 along the radial direction survive and perpendicular to it they cancel out? Yeah, that you could say. But there is no way for you to say that all of these electric fields, E1, E2, E3, will vectorially add up. When I look at the component, let's say for this one, I'm going to choose a coordinate axis where I'm going to call this x prime and I'm going to call this y prime. That might be a good axis to choose for this one. Or for this one, a good axis to choose might be, I'm going to call the radial direction x, and I'm going to choose this direction as y. I mean, I can always say that at all of these 6 points, the electric field will be radial. Do you see that from the symmetry? On the other hand, why? Because E1 and E3 have the same magnitude. Look, this distance and this distance are exactly the same. This magnitude and this magnitude of charge are exactly the same. So I know E1 and E3 will have the same magnitude, but when I look at the components, the component along this direction survives. This perpendicular component will cancel with the component of E3 that is pointing like this. Right? In the y prime direction. So it's true that all of the electric field at these 6 points will be radial, but there is no reason for me to believe that the electric field produced by this charge, which is only this much distance away, will somehow be, and the electric field produced by these farther charges will somehow work out to be the electric field produced by this farther charge and these closer charges. Do you see why would that be the case? There is no reason to believe that that will be the case. Please.
How are you able to determine that it wouldn't be the case?
Because the thing is, if you cannot prove that it will be the case, then in general it wouldn't be the case. Do you see what I'm saying? So the thing is, if you want, I can choose some distances. If you want, I can say that, let's say that this distance was a certain thing, 1 meter. Let's say that these distances were a certain thing, let's say 2 meters or something. I can choose this to be 2 meters. But the point is that if you cannot convince anybody that they are the same, then in general they are not. You see what I'm saying?
But how are we, it would take a significant amount of calculation to be able to show that they were the same, and a lot of complex geometry. How are we supposed to be able to do that in a minute?
Well, that is because the point is that in general they are not the same. This is not a quantitative question. I'm not trying to say to you, find the magnitude of electric field. I'm just saying that based upon what I have taught you in the past 2 classes, you should be able to say, and what you have learned in physics 1, which is that if suppose, there are 3 vectors, let's say all we are saying in this case is E1 and E3 have the same magnitude, right? So we are saying, you can call this E1 if you like. Similarly here, E2 and E3 have the same magnitude. If you like, you can call this E2, right? This thing has some magnitude, E1 has some magnitude, because this is some distance R1, if you like. These distances are R2. Here, R2s are totally different and R1 is totally different. All you can say by looking at this, that there is no way that in general, regardless of what these distances are, regardless of what is the radius of this circle, that electric field at this point and this point will work out to be the same. You have to just know this from vector addition, that there is no reason for you to say, here, basically what we are trying to say here is this. We are trying to say this, and you have to just know this from physics 1 and physics 2, that there is absolutely no reason for you to believe that if you have one vector like this, you have to find what is the net vector here at this point due to some vector here, due to So no, you are not supposed to find the magnitude, but this is just vector addition from physics 1 and physics 2, and you ought to be able to actually make a qualitative inference that no, in general this cannot be the same. So if you call this thing E1, and let's call both of these E2s, this is one situation. The other situation is like this. The other situation is some point here again. Let's call this thing E1 again. And there are 2 points. One of them might be here. The other point, which might be over here, E2, E2. The point is, these are the 2 situations. I just made, these were all they were looking like they were at an angle. I just straightened it out. Do you see that this is the farther distance? These are the 2 closer charges. So this is just like this, let's say. The middle one was farther. This is the case where this one charge is closer, these charges are farther away. And what I'm trying to say is that based upon what you've learned in physics, physics is not about really guessing, it's about thinking about what you've learned about vector addition and inferring that there is absolutely no reason to believe that regardless of what I have been given for any circle that I choose around it, this distance could be one thing, this distance could be one thing, this distance could be... The only thing I know is that these 2 distances are the same. This one is much larger. That distance is a lot smaller than these 2. There is no reason to believe that those 3 vectors will work out to be the same as this vector. There's no reason to believe in general this will be true. Okay? Because that's what it's saying. It's saying, is it always true? And the answer is no, it's not in general true. Go ahead, please.
It seems to me that since it's a circle, that the average distance from all 3 of the charges is equal out every point. Just the average of it. And that would make the magnitude.
Well, that's the thing. The important thing to remember, that's a very good point, what he's saying, and that's the way many students think. That's why I think, actually, I put this question in because you have to actually think about these points. So he made a very good point, which is that, he's saying, oh, since it's a circle, even though this distance is much larger than these 2 distances, wouldn't on an average somehow the distances wouldn't they all add up to the same thing? First of all, even if the electric field law was not 1 over r square law, but it was 1 over r, let's say that the electric field actually didn't go as 1 over r squared. We will see that we'll look at another quantity that will go as 1 over r, which is called potential. Notice that r is in the denominator here. You cannot say that I am adding up some distances. You're not trying to do this. You're not saying, oh, so E net will somehow depend upon R1 plus R2 plus R3, where R1, R2, R3 are these distances. They are not. Sorry. We are not trying to add up 3 distances here. What we are trying to do is we are trying to calculate an electric field which depends upon 1 over r squared. Do you see what I'm saying? So even if you say to me, suppose even if you say, hey, if this distance was 5 meters and this was 1 meter and this was 1 meter, the 3 of them add up to 5 plus 2, which is 7, and somehow there also it will add up to 7, does it mean that even if that were true, let's say, does it mean that the electric field contribution due to each of them will be the same? It goes as 1 over r squared. Do you see that? It doesn't depend upon adding up all the distances. Also, it's a vector quantity. Once you have found the electric field due to each of the charges, then you have to add them up like vectors, right? So I think this question is not quantitative. I'm not telling you to calculate a number. You can absolutely do it at home. But the point that he raised is an excellent question. And the point is that this is not what you do. You're not adding up distances. So even if the distances somehow added up to the same thing, it does not mean that the electric field will be the same. We are adding vectors. Not only are we adding vectors, we are adding vectors that go as 1 over r squared. Is that making sense? So if I told you, oh, there are 3 charges, here's 1 charge, there's 1 charge, and there's 1 charge, and what is the electric field here? And just because R1 plus R2 plus R3 turned out to be the same here as somewhere else over here, doesn't guarantee anything about the vector sum of the electric fields working out to be the same, right? Because we are not talking about adding distances. But that's an excellent point that people should keep in mind. That's what this conceptual question is trying to draw your attention to, that we are adding vectors, and we are adding vectors that go as 1 over r squared. Any questions about this? So obviously, one thing we see is that the magnitude of the net electric field is not the same at point A as all of the other points. It is the same at point A, C, and E, but not at B, D, and F. Will B, D, and F have the same electric field? Yes, they will have the same magnitude electric field, because you see that they have the same symmetry with respect to the charges. So you could guarantee that B, D, and F will have the same magnitude electric field. But that doesn't have to be the same as the magnitude of electric fields at A, C, and E. Does that make sense? So this is not a quantitative question. This is just a conceptual reasoning question.
I understand that, but I understand that it doesn't have the same electric field all around the circle. I don't feel that you've concretely shown that it doesn't. Like, I understand the reasoning that there's one point that's close, and then there are 2 points that are farther away, and that there's one point that's far away and 2 points that are close. But based on the geometry there, I don't see how the number of points, if you don't like go through, you can just say that it doesn't work. Like, I don't question that it doesn't work. Like,
Okay, you are saying, well, I mean, and that's why you will see that even in your homework, there are 2 kinds of questions that I assign to you. One kind of question is conceptual reasoning question, and one kind of question will be quantitative questions. So in one kind of question, you might just be asked to reason through something. You already saw that in chapter 21. Even chapter 22, you can see there are 2, 4, 3, 4, 5. Those questions, you might just have to say, which of these is greatest, or which of these is smallest. So you can make some conceptual reasoning arguments, and again, you don't necessarily have to calculate anything because there isn't time given to you. That's basically the point. Sorry, go ahead, please.
no, I understand.
But please, take the time at home to convince yourself by choosing some number. So choose some radius for the circle, choose some distance. So at home, you will have much more time, to turn it into a quantitative question, because you could have been given this question as a quantitative question, right? But then you will be given a lot more time. If you are given a question as a quantitative question, I'll give you 10 minutes to do this problem or something. But the thing is, you could at home say, oh, let me assume that each of these sides is 1 meter long. Let me assume that these 2 things are on x-axis, this is on y-axis. And let me actually assume that this radius of the circle is, let's say, 2 meters. And let me now try to figure out just 2 things. What is the electric field magnitude at A, and what is the electric field magnitude at B? Just 2 points, not very many. And just convince yourself that what we are saying makes sense. Because, I totally agree with what you're saying, and that is the reason why conceptual reasoning is not much easier than quantitative reasoning. That much I can guarantee you. What you're saying is a very good point, because conceptual reasoning is not easy, and I will show you later on also in the context of solving problems that when you have to do conceptual reasoning, you really need to know, what am I trying to find? I'm trying to find the vector sum of the electric field due to this charge, and this charge. The question is, does it necessarily work out to be the same here as here if I actually know the rules of adding vectors, and if I know what the electric field vector magnitude looks like for different charges, for different point charges, The thing is, this is a conceptual reasoning. I'm not telling you, oh, work this thing out quantitatively, because when you work things out quantitatively, oftentimes you can use certain rules and not even understand what you're doing, and you can get an answer that may be right, but you don't know what you did. When you're doing a conceptual reasoning, you have to think through much harder, because you have to really say, do I understand how to add vectors in physics 1? Are these vectors necessarily going to be the same? When each of these vectors has a magnitude that is given by this, a formula like this, where this could be R1 or R2 or R3. So conceptual reasoning is often much more difficult, and the thing is, this is true. You have seen this in your, you guys haven't taken MCAT exam, but pre-medical students take MCAT exam. You guys have probably seen it in any conceptual reasoning questions that you took in Physics 1 versus the quantitative reasoning ones, right? In quantitative reasoning ones, if you know the formula, many a times, even if you don't know why is it that it turns out that the potential here is higher than here, you use some formula and it works out that way. But if suppose you're asked, why is it that the potentiality is more here, or potential is higher, or why is it that the electric field is stronger here, that is a much more difficult question because it's asking you to reason about something. But in physics class, our goal is not just to teach you, some plug and chug. And I said this in the syllabus first thing, if you remember, look at the first line of your syllabus, that the goal of this course is to teach you both conceptual and quantitative problem solving and not just plug and chug. Okay, so this is a very important point. We are thinking about how to do this too. And the point is, so I can guarantee you by the end of this course, if you're really keeping up with things, you'll have a great time and you will learn a lot. You'll say in the end, I learned something about electricity and magnetism, and I learned some reasoning ability that I can actually transfer to my other courses. Because that would be my goal. My goal would be that something that you've learned here, you can actually use elsewhere as well. By the way, what about this thing? Electric field? Is the direction of electric field the same, the radii out at all points? Would you say that if I look at points here, would you say that the electric field would be radial, means straight out from the center at this point? But can you say about all these 6 points? Yes. So from the symmetry of the situation, the electric field will be straight out from the center at these 6 points, but not at any other point. For example, if you looked at some point over here, the electric field due to this charge will be like this. The electric field due to this charge will be like this. The electric field due to this charge will be like this. And there's no reason to believe that these E1, E2, E3 should work out to give me a radial direction. There'll be something like this, but it could be at an angle. It doesn't have to be perpendicular to the tangent. So the point that I'm trying to make is that the direction of the net electric field is radially out for the 6 points shown, but it is not radially out for all of the points on the circle. Right? So 1 is right, whereas 3 is not right. Also for 2, what did we say about 2? 2 is not correct because even though A has the same magnitude electric field at C as C and E, it doesn't have the same magnitude electric field as B, D, and F necessarily. So the correct answer here is then, yes, the correct answer then is just A. The direction of electric field is radially outward at the 6 points shown. So the correct answer is A, which looks like most of you got anyway, which is great. But even if you didn't get it right, think of it as learning opportunity. You have learned about these things in the last class, so you're still learning about it. So there is no need to feel discouraged. Think of it as a learning opportunity. Okay, here is something from the first class. It says a negatively charged insulating rod is brought near a metal sphere which is resting on an insulating stand. A grounding wire is connected to the sphere as shown. After some time, the charged rod is removed. Following that, the grounding wire is removed. Then, the net charge on the sphere is positive, negative, 0, not enough information, none of the above. Talk to a person next to you. You have 1 minute to answer this Here. You should look at this. Okay, so what you have to remember about this problem is that It says after some time the charged rod is removed. So you are first removing the charged rod and then you are removing the grounding wire, right? So therefore, what do you think will happen? The net charge on this thing should be 0. Do you remember? Because what will happen, if you think about the situation, here is what we said should happen. You bring this negatively charged thing here, it induces positive charge here, negative charge here. Now you put a grounding wire, this is the grounding wire. You see the electrons here are repelled by this rod, so the electrons in this case will go through the grounding wire to the ground, right? Now if you remove this rod, do the positive charges have any incentive to be next to each other? They don't. So what will happen? Electrons will come back from the ground, neutralize these things. This thing becomes neutral. So there's no net charge left on this thing. Now if you remove the grounding wire, you can see this whole thing is neutral. So the order in which you remove things is really important, right? Okay. So the correct answer here is C.
Quick question about that. The sphere started out at like positive or negative, and then you did that and then removed the insulating rod. Would it go back to neutral? Does it still-
Yes. So the question is a very good one. The point is you don't have to. So basically the question is he's asking something like this. Suppose if you had this thing which was already charged, let's say it was positive, right? You connect it to a grounding wire. What do you think will happen? Yeah, will it become neutral? Yeah, it will become neutral because these positive charges do want to run away. They do want to go somewhere, but they need a conducting path to flow. As soon as you connect this to the grounding wire, Earth is a huge conductor. If the electrons come from the ground and neutralize these things, it's true that now there are some positive charges left on Earth, but Earth is so huge that the positive charges are going to be so far away from each other, they won't feel each other's repulsion very much. You see what I'm saying? Because it's true that if you had electrons go there, then positive charges are left on Earth. But the point is, Earth is huge, positive charges are far away, repulsion is almost negligible. So yes, these things will neutralize. Any other questions, anybody? Okay. Let's look at the next question here. It says, a negatively charged insulating rod is brought in contact with a neutral insulating sphere resting on an insulating stand as shown in the figure. Then, A, some of the negative charge gets transferred to the insulating sphere and the charge gets uniformly distributed on its surface. B, some of the negative charge gets transferred to the insulating sphere and the charge stays localized at the point on the surface where the rod is touched. The insulating sphere becomes positively charged and the charge gets uniformly distributed on its surface. Insulating sphere becomes positively charged and the charge stays localized at the point on the surface where it was touched. Not enough information. Please talk to a person next to you.
What do you guys think? They want to be Oh, wait, yeah. Oh, wait, there's
Okay, what do you think is the answer here? The correct answer here is B, because some of the charge gets transferred, but it stays localized at the point where it was touched. Because remember, I mean, it's an insulator, right? So wherever you rub the thing, wherever you touch the thing, the charge will just go, a little bit charge can get transferred there, but it's not a conductor. There are no free electrons, so it's not like charges are moving from one atom to the other and spreading out. Does that make sense? And is everybody seeing that if charge gets transferred, it will become negatively charged? So the correct answer here is B. Okay, let's look at the next question. Okay, this time it's talking about a negatively charged insulating rod is brought in contact with a neutral metal sphere which is resting on an insulating stand as shown. The choices that you have to pick from are some of the negative charge gets transferred to the metal sphere and the charge gets uniformly distributed on the surface. B, some of the negative charge gets transferred to the metal sphere and the charge stays localized at the point on the surface where the rod was touched. Metal sphere becomes positively charged and the charge gets uniformly distributed. Metal sphere becomes positively charged and the charge stays localized at the point on the surface where the rod was touched. Not enough information, none of the above. Please talk to a person next to you. Hold it down
An insulating surface is
Okay, notice this time the thing is touched. Right? Is everybody noticing that there is a difference between touching something and not touching something? Well, no, I mean, I want to distinguish between this case and the induction case, right? Okay, so the correct answer is A here. Because in this case, if the metal sphere is touched with this negatively charged rod, this is metal sphere, right? And here you have a negatively charged rod. Some of the excess electrons from here will actually get transferred and they'll distribute themselves on the outer surface of this conductor, won't they? Not only will it transfer, it will uniformly distribute itself on the surface of the sphere. Is that making sense, folks? Okay. Any questions, anybody? Okay. Let's see if we have any more questions here. Okay, try a couple more. It says, two small objects, each with a net charge of plus q, exert a force of magnitude F on each other. We replace one of the objects with another charge, which is plus 4q. So instead of q, we replace it with 4q. The original magnitude of the force on charge q, suppose if the force there is F, we are calling it F, then what would be the force between these two charges? That's the question. And your choices are 16F, 4F, F, F over 4, other. Is everybody understanding what the question is? What is the magnitude of the force on this charge now compared to the previous case where it was called F? Talk to the person next to you.
And it's just one is what force
That's probably I know. I'm not good at it. She's the best friend. Yeah, that's the same thing. I think she's really
Alright, so it looks like everybody got this right. The correct answer is 4F, right? Because the force on both of them will will be equal in magnitude and opposite in direction, and it will be 4 times what it was before. Because remember, Coulomb's law says that the magnitude of the force between two charges is K, Q1, Q2 over R squared. If you make one of them 4F, the force on both will become 4 times more. Is that making sense? Great. Today, the first thing that we are going to talk about will be this concept of electric field line. So what is electric field line? If suppose you have some charge, you know that it produces some electric field around it. So for example, if I have a point charge, let's talk about electric field lines due to a point charge. So case 1 will be point charge. Here is the thing. If I ask you what is the electric field here, what will you say? What is the electric field here produced by this point charge plus Q? You will say its direction is away from you and its magnitude will be given by K, Q divided by this distance square, right? Similarly, if I ask you what's the magnitude of electric field here, you will say K, Q divided by this distance square and its direction is that way. If I ask you over here, you will say, oh, the direction is radially away, the direction is radially away, the direction is radially away, etc. The thing is, Michael Faraday was a famous scientist who did a lot of work related to electrostatics. He said, you know, it may be a good idea to actually join all these electric field lines at different places, electric fields at different places, and talk about electric field line. So electric field line for the point charge is just going to be these lines which are radially away from a positive charge and they are radially towards a negative point charge. So these are the electric field lines for a negative point charge. Now why are they useful? The reason they are useful is because they tell you two things, and again, they are not going to give you a number. They will not tell you how strong is the electric field, what is the exact magnitude of the electric field here or here or here. And if I don't draw a line here, it doesn't mean that there's no electric field there. I can draw a line and I can show you that there is electric field. So you only draw a certain number of electric field lines to show which way the electric field is pointing. And the good thing about these lines is that if you want to know what is the electric field here, you can say, oh, its direction I know for sure is this way. Right? What is the direction of electric field here? Oh, I know for sure it's this way. What about here? Draw another electric field line. Its direction is this way. What about magnitude? You cannot tell numbers by looking at electric field lines. What you can tell is where might electric field be stronger than other places. For example, wherever the electric field lines are denser, do you see close to this charge? If I look over here, are there more electric field lines than if I look, say, for example, here? Or, for example, if I look over here? So what you can say is, hey, the density of electric field lines, or how many electric field lines are there per unit, area, is more here, less as I go farther away, even less as I go farther away. That means the field is getting weaker as I go away from negative charge. That's all you can say. You cannot say exactly what is the number. If you wanted to know the exact number, then you have to say electric field magnitude is K, Q over R squared. And you need to know what that R is, right? To know the exact number for what is the magnitude. But you can roughly say the field is weaker here than it is over here. Now, this is the electric field due to point charges. Electric field lines due to point charges. What about electric field due to several point charges? Let's look at a configuration that is called an electric dipole. So today we are going to focus a lot of time on this case, case 2, and this is called electric dipole. Does anybody know what is an electric dipole from a chemistry class? Anybody? How would you explain to some friend or relative what an electric dipole is, please?
It's a difference of charge from one spot to another.
Okay. That's a good, any other thoughts on what an electric dipole might be, please?
Like on an atom, one time it'll be partially positive, one time it'll be partially negative. At one time
Good.
or another.
So the thing, very good. So both of you are correct. The point is, electric dipole is a positive charge separated from a negative charge, and they are exactly equal in magnitude. So a positive charge next to a negative charge, let's say the distance between these two is d. This configuration of two charges is called electric dipole. Now what he was explaining, for example, could happen in water. Water, it turns out, is an electric dipole. You know why water is an electric dipole? Because water consists of, water is H2O, so it has two hydrogen atoms and one oxygen atom. It turns out that the oxygen pulls the electrons more towards it. It has a greater affinity for electrons than hydrogen does, and so partially, not fully, partially the electron gets moved, there are partial negative charges that develop on oxygen and equal amount of positive charges that will develop on hydrogen. So if you like, you can think of water conceptually like this, as a dipole. Alright? Now, what would be the electric field lines for a dipole? Now, in order to figure out the electric field lines for a dipole, we need to figure out what is the net electric field at different points. Right? Because when I draw these lines, these are lines that are showing the net electric field. But look, for one charge, there was only one charge for which I had to draw the electric field lines, right? Now if I have two, I have to think about the electric field due to two. So let's think about it slowly, okay? What would be the direction of electric field, say for example, somewhere over here? On a straight line that is joining these two charges. Let's think slowly. So suppose over here, let's pick some point P. Which way is the electric field due to the negative charge? Towards it or away from it? Towards it. So this is the one due to the negative charge, let's call it E1. Which way is the electric field due to the positive charge at this point? Away from it. So this will be E2. Which of these is going to be stronger? Because E net at this point, let's call it point P, E net at point P will be, if this is my x direction, it's going to be E2 minus E1, right? Magnitude of E2 minus magnitude of E1. Which is bigger here? Is everybody agreeing that E1 is stronger? So that means what the net electric field EP will be which way? To the left. Very good. So I hope that everybody can see that the vector sum of E1 and E2, that means EP is this way. Right? And is that going to be the case for all points on this side? Is this charge going to always have a stronger influence there? It will, right? Because the electric field due to each charge is K Q over R squared due to each point charge. And since R for these points here is less due to this charge than due to this charge, the negative charge has more influence in this region. Right? Similarly, what about this case? Suppose I'm looking at some points over here. The electric field due to the positive charge, E2 is like this. Is that making sense? The electric field due to the, let's call it Q2, and this is Q1. Which way is the electric field at this point due to negative Q or Q1? It's towards it, right? Remember, negative charges always have electric fields towards them. So I know that E1 is that way. Again, which one do you think what would be the net electric field at this point, E prime? It will be E1 minus E2. But in this case, which one is bigger? E2. Is everybody seeing that the net electric field due to the vector sum of these two is going to turn out to be in the negative x direction? This is going to be EP prime. Right, if you do this? Is everybody seeing this is going to turn out to be negative? And if this turns out to be negative, that means it's this way, in the negative x direction. I chose this to be positive. And that will be the case for any point. If you ask me here, etc. Everywhere the electric field is going to be pointing, the net electric field will be pointing this way. Okay, what about at the perpendicular bisector? In fact, this was one of the questions in the concept test that I asked you. Which way will it be, folks? Somebody from the third row. at any point on the perpendicular bisector, this was the first question in your concept test. Then tell me, if I ask you on the perpendicular bisector, what is the direction of electric field here? Direction of electric field here, direction of electric field here, 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 etc. Third row. Go ahead, please.
Is it that way?
Very good. Because you can see that the electric field due to this one is going to be this way. We can call it E2. The electric field due to the negative charge is going to be towards it. We can call it E1. We can take the component of this along x direction and along y direction. If I do that, the component of E2 will be this way and that way. The component of E1 will be this way and that way. These two cancel out completely, right? Because these two distances are equal and these charges have the same magnitude. So E2 and E1 have the same magnitude. So does everybody see that the net electric field will always be like this? Okay, so in other words, if you ask me for what is the direction of the net electric field here or here or here, anywhere on the perpendicular bisector, it will turn out to be like this. What about right at the center here? Same, right? That's what you were asked earlier in that concept test, remember? Is everybody clear on this? Okay, good. What about at some other point? Suppose you ask me what is the direction of electric field here? Hey, I can still do it. I do have to do more work. How will I do it? Due to negative, again, the same story. So due to negative charge, the electric field will be towards it. Due to positive charge, the electric field will be away from it. So I can call it E2. This is my E1. If I have two vectors like this, again, what should I do? Is everybody, let me not make it too messy. But the point is, this is minus Q and this is plus Q. And I'm trying to figure out what is the electric field at this point over here due to each of these. And I'm saying, if I call this Q1, the electric field due to that will be towards it because it's negative. Due to this one, the electric field will be away from it, E2. At this point, I have to again take vector components. E2 will have components like this, etc. If you work this out, which one has more? Is E1 and the component of E2. Let's call this thing E2y. This is E2x. Which one is going to be bigger, E1 or E2y? Let's say E1 is, E1 has two components also, let's say. E1 is like this, so E1 will have a component, E1x. E1y. Who wants to tell me how would E1y and E2y compare? E1y is bigger?
Yeah.
And the reason you are saying that is because, first of all, this is closer, this distance is less than this distance, right? And the charges are the same. Both of them have the same magnitude. Remember, electric, do you understand what I'm trying to say? So the point is that you can find the direction of the net electric field. So basically the net electric field will have something, E1y, let's say like this, minus E2y, which is like this. And then you have E2x and E1x. So you have E2x and E1x. And you can find the net of this, and the net might turn out to be, for all you know, something like this. Right? I'm not going to work out the math right now, but this is something what you might find, that the net is like this. So instead of all of this mess here, I could just replace all of this mess with an E net, let's say, pointing like this. So now how do I draw an electric field line? So basically, electric field line will be if I join all of those things. Remember I said that I can draw an electric field line by knowing, oh, this is the direction of electric field, direction of electric field, direction of... If I join all of this, I get the electric field line, right? In this case, I can do exactly the same kind of thing. And if you do that, this is what you will find. You will find that the electric field lines always point away from negative or positive charge towards negative charge. In this case, you understand the broader meaning of electric field line also. What I have done is I have drawn the electric field line due to an electric dipole. And now, if you ask me, what is the direction of electric field, let's say over here? What I have to do is first look at the direction of the electric field line, which is like this, and then draw a tangent here. If I draw a tangent here, that will give me the direction of electric field at this point. You know, this point might be this point that we were discussing. For all you know, I'm just saying, okay? If you were asked, what is the direction of electric field over here? What will you do folks? Draw a tangent to the electric field line, and which way will the arrow be pointing? You know, roughly the way the electric field line points. So E will be like, so E at this point is tangent like this. That's the direction. Okay, tell me, what about the direction of electric field at the center between the two dipoles? See, this one is a straight line, so you know tangent to a straight line is along the straight line, right? Isn't that true? So here the electric field is pointing like this. What about at any point on the perpendicular bisector? What about over here? If you draw a tangent, do you see the electric field is like this? What about over here? Again, you draw a tangent, and notice this is exactly what we said. We said that the electric field on the perpendicular bisector anywhere will be pointing like that. Isn't that true? Will always be. So over here, you can draw a tangent like this. What about over here? Somebody from the last row. What would be the direction of electric field there? Please go ahead, folks. It's a friendly class. I draw a tangent and then
Down to the right.
yeah, it will be like this. So that would be the direction of electric field at this point. Now you can also see another thing. Do you see that lines are closer together here than say they are farther away? And that would mean that the electric field is stronger here than it is over here. But again, if you wanted to know exactly, tell me what is the magnitude of electric field in Newton per Coulomb, you cannot get it from electric field lines. What will you have to do? You literally will have to do calculation like this, you know. You have to make some calculation like this and say, okay, E2 will be KQ divided by R2 square, E1 will be KQ divided by R1 square, etc. You know, something like this. And that's how you will do it. And in these cases, where things might be at an angle, if you're finding the electric field here, you know the direction of electric field will be the tangent to this here, but the magnitude is more complicated, right? You'll have to say, oh, due to this charge, the electric field E2 will be like this towards it. Due to this positive charge, E1 will be like this. And then you have to find the vector sum of these. This is not a simple sum like this. This is the only time that you can do a simple sum like this is if those two electric fields are in a straight line, right? Collinear, then there's no cosine theta, sine theta to think about. Otherwise, you have to be more careful. Is everybody clear on this? Now, here is the thing. Notice some really important thing about electric field lines. First, can they cross?
No.
Why not? They can't. You're right. They cannot cross. But why? What will be the problem if they cross? Go ahead, please.
Wasn't it because they all have certain strengths, I guess? Like,
yeah, and also the important thing is that if two electric field lines cross, suppose if I told you, oh, this electric field line is going this way and then this one's going like this, at this point, you can draw a tangent like this and then you can draw a tangent like this. That would say the net electric field here is pointing that way or this way. How can that be? The net electric field due to these two charges at this point cannot be pointing in two different directions, right? The vector sum of the electric field due to these two can only be in one direction. So no, electric field lines cannot cross. Because if they cross, then you're saying the tangent has two different directions at a point. That would say, you're saying E net is either this way or this way due to these two charges, which does not make sense, right? The other thing to note is electric field lines always start at positive. Do you see they're always emanating from positive charges and they always end at negative charge. So the thing is, this is always something that you should remember, that positive charges are sources of electric field lines and negative charges are the sinks. That's where the electric field lines end. Now you might say, this thing again is looking very qualitative to me, like what you were saying earlier, and it's true, it's qualitative. For example, if suppose you have this situation. Suppose you have, a plus Q charge here, you have a minus 2Q charge here, and the point is, how would you draw the electric field lines for these two things? Again, one thing that you know is that electric field lines will start from positive, they end at negative. Now you also should know that there are twice as many electric field lines that you should be drawing for the negative 2Q charge, because it's twice as strong as this one. You see what I'm saying? So if you decided to draw 2 electric field lines for this, you should be drawing 1, 2, 3, 4 for this one. If you decided to draw 4 for this one, you're trying to draw 4 electric field lines going out of this, then you should be drawing 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 electric field lines going into minus 2Q. But the point is, this is just a schematic thing that gives you an idea and tells you, hey, this thing is twice as strong as this, and that's why I'm drawing more lines here than this. But if your friend wanted to draw 16 lines here and 32 electric field lines there, there's nothing wrong with it, because it's just a representation anyway. Please.
That line that goes out from the left to the positive charge, why would it start coming back to the right?
You over here?
No, on the left side.
Here?
Yeah.
No, here it's actually going out, right?
Yeah. But why would it come back to the right?
Why will it come back to the right like this? Okay, that's exactly what I'm saying. That the way to understand this is, so at least that's a good point, and let's think about it. Why will it come back? One thing that you can see is that over here, if I draw a tangent, it's going like this, right? Over here, if I draw a tangent, it's going like this. And that's exactly what we said. We said at every point on this straight line, it should be pointing that way, okay? Now, if I ask you, tell me the electric field over here. How will I do it? I'll say due to this positive charge, it's like this. Due to this negative charge, it is this way. Which one do you think is stronger here? This one, right? You would say that this one is stronger. So this charge due to, let's say, what name did we give? Q2? Let's say this, we call this Q1. So E2 is stronger than E1, right? Do you see which way will be roughly the vector sum of these two? Will it be something like this?
Up and to the left.
Yeah, I mean, it depends on, you have to take the component of this like this, like this. You have to take the component of this like this and like this, and then you have to add up this component with this component with this, right? And then find the vector sum, and you can see, and now choose another point over here and see which way is the electric field due to the positive charge here, which way is the electric field due to negative charge here. If you work that out, and if you find the electric field at different point, you will see that it will show this behavior, that closer to this point where it makes sense, like if on this straight line, joining the charges, if it's pointing this way, doesn't it make sense that over here, it will slightly curve up?
Yeah, but shouldn't the left of the positive charge still be going in the negative x direction and not positive?
It does. So in other words, sorry, what I'm trying to say is that along this straight line, it does go this way, right? And then, but again, if I ask you what would find the electric field here at this point, due to positive charge, you will say it's pointing this way. Due to negative charge, you will say it's pointing that way. Then you find the vector sum of the two, and you will see the vector sum of the two is pointing this way, right? And that's the direction of the net electric field. Similarly, if you look at a point above the axis, you will see that this charge has its influence like this. This charge has its influence like this. If you find the vector sum, it will be along the tangent. Right? So above and below this thing where it's going like this, they start curving this way or that way based upon at which angle is the influence of these two charges. right? So at every point, the electric field line is giving you the net electric field due to these charges. Any more questions? Please.
In the case with the unequal magnitudes, the lines to negative 2 just come out of nowhere.
No, they must be coming from some other positive charges that are not shown in your diagram. So electric field lines always, that's a very good point. Electric field lines always start from positive charges. They always end at negative charges, always. So they couldn't be coming from nowhere. These things are coming from some other positive charges somewhere that may not be very close. It could be like extremely far away, so you don't really see it in your picture. But that's a very good point. These lines are not coming from nowhere. They must be coming from some positive charges. All right? Very good point. And similarly, if I'm showing these lines, they'll keep going till they meet some negative charges. So electric field lines will always end in negative charges, always start at positive charges. Please.
For the 2 times Q, it's going to curve that way.
Okay, exactly how it will curve is will depend upon where those charges are that are actually originating it, which I haven't drawn here. So it could be very different depending upon the configuration of all the other charges that I haven't shown. I've only shown you 2 of them. Very good points. Any other thing? Okay, it looks like you guys have a good conceptual feel for things. Let's become quantitative. So let's now try to figure out how to find the magnitude of electric field. And let's first try to figure out how to find the magnitude of electric field along the line joining these 2 charges on a dipole, and then we will find it on the perpendicular bisector. So this time we are going to calculate numbers. But I hope you have a conceptual feel for what we are doing. So electric field on the axis of dipole. So what do I mean by axis? So this is plus Q, this is minus Q, this is the distance d between the 2 charges that form the dipole. And by axis I mean the straight line that is joining the positive and negative charges. Okay? Let's say we have to find the electric field magnitude at some point P over here. This point P is at a distance, let's say this distance from the negative charge, we give it a name R minus. Alright? And let's say that the distance from the positive charge is R plus, which is this distance. Just to be consistent with your book, let's actually find it on the same side on which they found the electric fields. Okay, so I think what we are going to do is we are going to be consistent with your textbook. And so in your textbook, they found they call this charge positive here. It doesn't really matter. They call this charge negative. So let's take this plus and minus. So in other words, the point P was closer to the positive charge. It really doesn't matter. Either way, you should be able to do it, shouldn't you? But I'm just saying, let's use exactly the same notation that they used in your book, because of the fact that when you look at your book, it will make much more sense. But it's the same. So let's keep this point P right now closer to the positive charge. Not important, but just consistent with your book. All right? Let's call this x-axis. I think also in your book they call it the z-axis because they keep the dipole vertical. Let me make it horizontal. It's good for us to use different notations a little bit at least. Okay, so here is the thing. Let's say that the distance from the center of this dipole to this point P is r. Suppose this distance is r. Is everybody understanding the goal? The goal is, what is the magnitude and direction of electric field at point P due to this dipole, consisting of these 2 charges? So if this is the distance r, we have to find this answer in terms of r. So that means point P is at a distance r from the center of the dipole. Who wants to tell me how can I write R plus in terms of R and D. D is the distance between plus and minus charges in the dipole. Anybody, folks? R plus is equal to what? Huh? This is equal to R, and then?
Minus d over 2.
Excellent. Minus d over 2, because the thing is, if this total distance is d, then half of this distance must be d over 2. So then, does everybody see that R plus is equal to R minus d over 2? Right? Who wants to tell me how to write R minus? In terms of R and D, because those are two things that are given to you. So in your thing, yeah, go ahead please.
R plus
Excellent. R plus d over 2. Does that make sense to everybody? So because in your work, you may be given, oh, the distance between the positive and negative charges on water, on the dipole formed by water is something. D is given. So you know what is d over 2 in this case, and you are given, you are told, find the electric field at a distance r away from the center of the dipole. So we need to get all of the answers in terms of, so we need E at point P in terms of Q, R, and D. Is everybody clear what we are looking for? Okay, so first of all, let's figure out what would be, how to figure out the direction of the electric field. What would be the direction of electric field due to positive charge? Is everybody seeing positive charge will produce its electric field away from it? Let's give it a name, E plus. Negative charge at this point will have its electric field towards it, right? Do you see that? So E plus and E minus are pointing opposite. This is, anyway, this is R plus, so E plus, E minus is this way. Is everybody clear on this, that E minus is that way because this charge is over there? So if this is my positive x direction, I hope everybody is agreeing with me that the electric field will be E plus minus E minus. This is the electric field at point P. Since they're pointing in opposite direction at that point, right, due to the two charges? Okay, great. What are these things? This should be equal to K. K is that constant. In SI unit, it is 9 times 10 power 9. And then Q is the charge, magnitude of charge divided by, what is the distance from the plus charge? Anybody from the fourth row? What is the distance of the point that we are finding the electric field from the plus charge?
R minus d over 2.
Yeah, it is from the plus charge, sorry. Sorry, isn't this positive? That is positive. We chose that to be positive. This is my negative charge. Sorry about that. Can you please fix it in your notes? All right. So from the plus charge, the distance is R plus, which we said is R minus d over 2. Thanks. So this is R plus square, and this will be K Q divided by R minus square, which can be written as K Q. What is R plus square? We already said this is R minus d over 2 square. This is R plus d over 2 square. Is everybody with me? Okay, now here is the thing. If I wanted to pull out R from here, what will happen? So I would like to pull the R out from here. So EP then will be K Q divided by, if I pulled out R, do you see that since there's a square, I have to pull out R square. What will this become? This will become 1 minus, do you see this will become d over 2R. Okay, and here what do we have? We have K Q R square D plus, sorry, this is 1 plus D over 2R squared. That's U. Okay, let's pull out things that are common. So I can see that between the two terms, I have this thing as common, KQ over R squared. Do you see that? Is everybody seeing that's common? And then what do I have? I have this and I have this. So I have 1 minus D over 2R squared minus 1 over 1 plus D over 2R squared. Okay, all we have to do at this point is simplify this expression a little bit, which we will do. Now I want somebody to remind us what is this. Does anybody remember what is this? A plus B times A minus B? Huh? Can I write it as A square minus? Yeah, A square minus B. So, I mean, A plus B times A minus B can be written as A square minus B square, right? Now, if suppose I had, A plus B square, A minus B, the whole thing square, then you see I can write it as A square minus B square, and then the whole thing square. I'm not doing anything fancy. I'm just saying if you square this side, you must square this side as well. Right? As simple as that. So here, what I'm going to do, I have these two things. I have to find the LCM, lowest common denominator. Do you know how to solve these things? So I have to find the lowest common denominator. And you see this is like A minus B, A plus B. In fact, what we have is A minus B square, A plus B square. So you can see that what I will end up with is something like this. I will end up with this 1 minus D over 2R square times 1 plus D over 2R square. This is the common denominator, lowest common denominator. Then do you see that here 1 will get multiplied by this? So I'll have 1 plus D over 2R square minus 1 minus D over 2R square. Is everybody with me? Then using this fact, I can write the denominator like this. I can write this as K Q divided by R square, and in the denominator I can make use of what I just showed you over there to write this as this. I'm just making use of this. This is my A, this is my B, this is A minus B, this is A plus B. Okay? In the numerator I have that. How do I find that? Let's work the numerator out. So in the numerator we have, what is this thing folks? A plus B square is A square plus B square plus 2AB. Right? So let's work this out. A plus B square would be 1 plus B over 2R square plus 2 times D over 2R. And then I have minus this thing, and that thing is 1 square plus D over 2R square minus 2D over 2R. That's you. Is everybody with me? Alright, so then what is this equal to? This is K cubed over R square. Notice in the numerator, do you see this 1 will get cancelled with this minus 1? Similarly, this D over 2R square will get cancelled with minus D over 2R square. This and this will get cancelled. And all I'll be left, notice that from numerator and denominator, this 2 get cancelled. So all I'll be left with in the numerator will be, excellent, 2D divided by R. And in the denominator, I have this mess. 1 minus D over 2R squared whole square. and this is my final answer actually. Notice that this r along with this r square will make it what? R cubed. Can I remove this from here and make it r cubed? This is it. So one thing that you should notice is that the electric field, this is the EP due to a dipole. Electric field due to a dipole on its axis. And remember, I told you axis means the straight line that joins the two charges. Now here is the thing, and we were looking at a point which was to the right of the positive charge. Now, can we simplify this expression? Suppose if I told you the place where we are trying to find the electric field, r, at a distance r away from the center of the dipole, is very, very large compared to the distance between the positive and negative charges. So suppose, let me teach you how to make approximation. So let's make approximation. So let's say that r was a lot greater than b. This greater than means a lot greater than b. That means the point where we were trying to find the point P where we were trying to find the electric field due to the dipole was very far away compared to the distance between the positive and negative charges. What would be a good approximation here? Anybody? Well, no, it's not so far away that you can put a 0 there. That's not, I'm just saying make the first approximation. You know, it's not so far away that we can just say, oh, it doesn't matter, if charges are negligible, we can go home. That's not the point. I'm just saying, what would be the first approximation that we can make to simplify that expression if r was a lot larger than b? But if we still wanted to find what is the electric field due to a dipole, please.
That d over 2r to the quantity squared compared to 1 will be very small to 1.
Excellent. What we, in this particular case, what we can say is that if r is like $1 million compared to this thing which might be 1 cent, 1 over 1 million can be ignored compared to 1. So then this thing can just be dropped. And 1 square will just be 1. So in this case, the electric field at point P, and if I put a wiggle like this, means approximately equal to, is approximately equal to K Q 2D divided by R cubed. Is everybody seeing that if that is the case, this would mean, this implies that D over 2R, you know, is a lot less than 1. Right? And so we just threw out, we just said, hey, this is almost 0 compared to 1. Throw that out. Okay, now the other thing, so this is the electric field of a dipole at a distance r which is much, much greater than d on the axis. Notice, is there a major difference between this expression and the electric field due to one single point charge? What is one major difference? Look at the r dependence. Here the electric field is falling off as 1 over r cubed, not as 1 over r square, but 1 over r cubed, right? Do you remember? If there was just one point charge, the electric field is going to fall off as 1 over r square. So if you go twice the distance, electric field will become 1/4 in that case. Here, if you go twice the distance, the electric field will fall off to 1/8, because you know if r goes to 2r cubed will be 2 cubed is 8. So if you go twice the distance from the dipole, if r goes to 2r, your electric field will fall off as to 1/8 times what it was at a distance r away. If you go to 2r, right? Are you seeing a difference in how the electric field falls off here as compared to the case of a point charge? You are? Okay, that's good. The other thing is, I can write this thing in terms of a new term. I'm going to define a new term that is going to be called the electric dipole moment. So let's define electric dipole moment. How am I going to define it? It's a vector quantity P which is equal to Q times D, and now I'm going to call D a vector. How can you call D a vector? If this is a negative charge Q and this is a positive charge Q, then electric dipole moment P is pointing from the negative to the positive charge, and I'm going to call D a vector. D is the now not just the distance between the two, D is a vector that points from negative towards the positive charge. Is everybody understanding what the electric dipole vector is now? It's just a simple definition, just to simplify, please.
Wouldn't it go the opposite way?
No, this is the way it's defined. So it is always defined, electric dipole moment is always defined from the negative charge towards the positive charge. There's nothing wrong in defining things in a certain way, but if everybody has chosen it this way, let's stick with it, right? If we don't define it the same way that people in the past have chosen, then they'll say, oh, we can't understand your definition. If we were the first ones to define it, we could have defined it the way you are saying we should define it, because there's nothing sacred about defining something in a certain way. Okay, if that's the case, then what can I write the electric field P vector as? Can I say it's K, 2K, 2 times K, QD, can I call it P divided by R cubed? Look at the direction of the electric field. Which way was the electric field? Look, the electric field was pointing, we said the positive charge will produce its electric field this way, the negative charge will produce its electric field this way. The net electric field turned out to be in the positive x direction. Do you see that the sign here is positive? Right? And is that the direction of P? See, P is pointing in this direction. The electric dipole moment is pointing from negative to positive charge this way. And that's what we have chosen to be the positive x direction. So we can call EP equal to 2kP over R cubed. And I hope that everybody remembers that K is just a constant, which is 1 over 4 pi epsilon 0. Right? Epsilon 0 was that permittivity constant of free space. Any questions about this, folks? Okay, can we find the electric field at some point from a dipole on the perpendicular bisector quantitatively? I'll just set this one up and I'll let you do it at home. But yeah, it is again not a difficult thing at all. So if we were to find the electric field quantitatively, say at some point P, which was over there, and what we have been given is this. We have been told that, let's say that this distance here is L, the distance between positive and negative charge is D. These charges are plus, minus Q and plus Q. And the question is asking, find EP in terms of Q, L, and D. Do you think we can do it, folks? Yeah, it's very simple. We have conceptually done it several times. Let's just do it quantitatively. It's not a difficult thing at all. What will we have to do? Due to negative charge, the electric field at this point will be? Will it be towards it?
Yeah.
Yeah, very good. So it's going to be along the line joining this point to the charge. So let's call it Q2. Let's call it Q1. So the point is, E2 is going to be like this. E1 will be which way? If this is a positive charge, its influence at this point, the electric field will be away from the positive charge. So it will be this one, this way. Okay. Now, is everybody agreeing again that if I take the component of E1, and let's say that this is my positive x direction, and this is my positive y direction, then the component of E1 along the negative x direction and negative y direction will be like this. Component of E2 along the negative x direction will be like this, and negative y direction will be like this. Right? Is everybody agreeing that the y components will cancel out of E1 and E2? Because E1 and E2 have equal magnitude. Because we are talking about perpendicular bisector, these charges are equal, these distances are equal. Let's call these distances R. So then, the only component that survives will be the horizontal component, right? So that will be, if we decide to call, let's say this angle is what we are calling theta. So this is our angle theta. Then what does that say? Which angle is theta then? This one, right? If we decide, or you could call this thing theta, it doesn't really matter. If we call this thing theta, then can we find the components? Which component is this? Is that going to be E1 sine theta and E2 sine theta? It will be, right? And we can say that E net is going to be equal to minus E1 sine theta minus E2 sine theta, which can be written as minus 2 times E1 sine theta. Is that making sense, folks? Yeah? Okay, who wants to tell me what is the magnitude of E1? Because I'm going to, at this point, let you guys do most of the work. E1 will be K times Q divided by which distance square? R square, right? And what is R square in terms of things we know? L and D. Can I write R square is equal to L square plus D over 2 square root, R. So this thing will be L square plus D over 2 square. Wouldn't it? And what will be sine theta? Anybody wants to tell me what is sine theta from this triangle? Sine of the angle is? Huh? Anybody wants to tell me what is sine of the angle from here? This is d over 2, right? D over 2 divided by? Yeah, square root of L square plus D over 2 square, right? So just put these two things in here, and that's it. That's your answer. Is that making sense to everybody? That is the answer. That's your electric field at this perpendicular bisector over here in terms of Q, L, and theta. Q, L, and D. All right, have a great day, folks.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.